Alright class, today we are moving on to 3.3, which is deductive reasoning. So read along with, as I read this out loud, our learning intention for the day is I am learning how to use Venn diagrams to organize information and make logical conclusions, and how to find counterexamples to show a conclusion might be false. Hopefully by the end of this lesson, you're going to be able to say that I can explain what deductive reasoning is and how it differs from inductive reasoning. I can identify valid and invalid arguments. I can recognize the structure of a valid deductive argument and explain why it is valid. And I can construct my own logical argument using deductive reasoning. Told you this was a logic chapter, and this is one of those sections that's going to test you a little bit, okay? So last section we talked about inductive reasoning with the converse, inverse, all those. Today we're looking at deductive reasoning, which is the process of reasoning logically and drawing a conclusion from given facts and statements. The first thing we're going to look at is the law of detachment. This law states that given a conditional statement, if the hypothesis is true, then the conclusion is also true. Now, there's a special way that they write this. Right? So, we're used to seeing this P then Q. We did that last section. That's our conditional statement. So, the law of detachment says that the hypothesis P, if that's true, all we're going to put is a P over, and then we're going to draw these three little dots. Okay? Q. That is the law of detachment in symbol form. How often are you going to need to know that? Honestly, probably not a whole lot. I don't believe you're going to see that very often, but it's just something to know. That's how it's written. So again, when we're looking at law of detachment and we're trying to figure out if something is valid, we'll get to this here in a second. If the hypothesis is true, the conclusion is true. So, use the law of detachment to give a valid conclusion. If not possible, write no valid conclusion. So our first one, if a quadrilateral is a rhombus, then it is also a parallelogram. They give us a statement, quadrilateral ABCD is a rhombus. So we're going to use our given statement, if the quadrilateral is a rhombus, then it's also a parallelogram. We're going to use that to make a valid conclusion about quadrilateral ABCD. In our given, we said if it's a rhombus, then it's a parallelogram. We were given a statement that quadrilateral ABCD is a rhombus, so we can say quadrilateral ABCD is also a parallelogram. No math, no nothing, just if the hypothesis is true, the conclusion is true. We were given a statement that this quadrilateral was a rhombus, so we were also able to say it was a parallelogram. For our next one here, our statement, our if P then Q, is if you are 18 years old, then you can register to vote. The statement we were given was that Olivia is not 18 years old. So is our hypothesis true? Olivia is not 18 years old. Does that make this first statement true? No. So we would say no valid conclusion. When you're looking at the law of detachment, if the first part, if the hypothesis is not true, you're done. You don't have to think anymore. No valid conclusion. I want you to take a second. Try that last one. Just give it a chance. Pause the video, and we'll be back in a second. All right, let's get back to it. If the sum of the measures of two angles is 90 degrees, then they're complementary. We did this last chapter. We know when two angles add up to 90 degrees, they're complementary. So the statement they gave us is the measure of angle J is 58 degrees, and the measure of angle K is 32 degrees. So, do those two angle measures add up to 90? Is 58 plus 32 90? I hope you're saying yes. Excuse me. So, our statement, 58, 32, we add those together, we get 90. This and this are true. So we can say that angle J and angle K are complementary. So that one was relatively simple. Again, you took the statement they gave us, looked at the conditional statement above it to see if they matched. Now we're going to look at the law of syllogism. I believe that's how you say it. Syllogism. Maybe it's syllogism. There's two L's. So, I'm not sure. I'll be honest with you. You guys know I'm not an English teacher. Okay. The law of syllogism allows you to make a conclusion from two conditional statements. So instead of just having one statement like we had up top, now we're going to be looking at two different statements, and we're going to combine those. So the law of syllogism allows you to draw a conclusion from two conditional statements in which the conclusion of the first statement is the hypothesis of the second statement. So if we're looking at that as our conditional statements that we've been working on, we have if P then Q, if Q then R, then we're able to say P, if P then R. That's all we're saying. We're skipping that middleman. We're skipping the Q and going straight from P to R. We're going to use the law of syllogism to give a valid conclusion. If it's not possible, write no valid conclusion. So, the first statement we're given is if a number is divisible by 12, then it's divisible by 6. Second statement is if a number is divisible by 6, then it's divisible by 3. All we're doing is we're taking the conclusion of the first one and the hypothesis of the second one, and we're getting rid of it. So all we care about is the hypothesis of the first. If a number is divisible by 12, then it is divisible by 3. That's it. That's the law of syllogism. If your conclusion of the first one matches the conclusion of the second one, or the hypothesis of the second one, you're able to say hypothesis of the first, conclusion of the second. So again, it is a rectangle. It's a rectangle. So we're able to say if a quadrilateral is a square, hypothesis of the first, then it has 4 right angles. Conclusion of the second. That's all the law of syllogism says. This up here makes it sound can make it sound confusing. All we're doing is getting rid of the things that are the same. That's it. All right. Let's move on to the next page. Next page is something that you guys have seen before. Venn diagrams. Things that compare them using circles. There's 3 main types of Venn diagrams that we're going to look at. One where you have a circle inside of a circle. All elements of P are elements of Q. So, one example could be P represents all the 8th grade students at Kennedy Middle School. Q represents all of the students at Kennedy Middle School. If you're an 8th grade student at Kennedy Middle School, you are part of the entire school. Okay? Then you have the normal Venn diagram that you're used to seeing, where some elements of P are elements of Q. I don't really like that wording. I would say that some elements of P and Q are the same. I would prefer some elements of, so I'm going to write up here, P and Q could be the same. That's what I would prefer. P and Q could be the same. And the last one is when there's no relationship between P and Q. Nothing overlaps. All right? So let's draw some Venn diagrams real quick. Some students who play football also take band. So is that saying that all the students are the same? Which one do you think that would be? Do you think that would be the first type, the second type, or the third type? Some of it matches. So what that tells me is that we should have something similar to our second one. We should have a circle on this side. Don't make fun of my circles. Circle on this side. One side is football. One side is band. Where they overlap is those students who play football and also take band. So, all right. Next one. Every natural number is a whole number. Do they have some in common, nothing in common, or is one completely part of the other? Your key word there is every. So we're going to have one big circle, one little circle. Which part is the smaller circle? Which one is every? That's our natural numbers. The big circle is the whole numbers. The last example, irrational numbers are never rational numbers. There's no correlation between the two. There's no relation. So that's the one that's right above it. One circle over here, one circle over here. We've got irrational and rational. In Venn diagrams, we're looking at one of these 3. Next little bit here, shade the indicated region on the Venn diagram. All right, seems pretty straightforward. Q. Where's Q at here? Oh, right here. So we're just going to shade that. We're just shading that. That's your job. All right. P What does the upwards arrow mean? And. Not Q. Okay, so that's a little different. So we know we're shading P, but we're also shading not Q. Well, not Q would not include anything from circle Q. So we're going to leave circle Q alone, which means we're just going to shade that little part of a circle. We're not going to do the overlap. It's just P. And finally, this last one, P, downwards arrow, or Q and R. So, because it's or P, we remember from last section that or means we only have to prove one of them. Only one of them has to be true. So we're going to shade all of P right off the bat because that's on its own and part of an or statement. So we're going to shade all of P. Now we have to shade Q and R. So what section is both Q and R? Well, it's this little section right here. And I've been saying since we started this chapter, there's very little math to this. It's all logic. It's understanding. All right. I know this might not be the most fun thing in the world, but we got to get through it. Last little bit here. Describe each diagram using a conditional or compound statement. So we can write it as an if-then statement, or we can just write what we see. So in this first one, volleyball, piano lessons. That kind of looks like, when we were up here at the top, some students who play football also take band. So what if we were to say, we don't know if these are students or what, so let's just say some people, let's look back up here, who play volleyball. Up here we had also take band. Well, the other side is also take piano lessons. The second one. All we have shaded is this left side, not the middle, not here. Well, that kind of looks like this right here. P and not Q. So here's P and not this. So there are months with 31 days, and, because again, we're looking at this one right here, looks very similar to this, and months that we're looking for not, do not start with J. You're going to be able to use a lot of these for this. Okay. How about this next one? Looks like the opposite of this. So instead of not Q, we're going to have not P. So this is going to be not P and Q. So we can say, again, we're talking freshmen, so we're talking students. Some students do not take art and are freshmen. Finally, our last one. Everything is shaded. What that tells us is it only has to meet one of these requirements. It either has to be a multiple of 7 or be an even number. So what does that tell me? This is P or Q. Numbers, because we're talking numbers obviously, are multiples of 7 or they are even numbers. Now, I didn't ask you to do this, but can you find a counterexample for this? Can you find a time where there's a number that is neither a multiple of 7 or an even number? Is there any number that you can think of that's not a multiple of 7 or an even number? If you can figure out any number that is not a multiple of 7 or an even number, that is a counterexample. So you can say 1. You can say 3. You can say 5. You can say 9. You can say 11. You can say 13. You can say 15. And you can keep going. There are a lot of things that make this not true. So in the future, you're going to have to find those counterexamples. There have already been some homework assignments that have asked you for that counterexample. That's what it means when it's asking for a counterexample. Name something that makes your statement false. Good job today, y'all. This is 3-3. Make sure you take a look at that homework. If you have questions, please ask.